So it's always fun being the afternoon spot after lunch spot on a Friday, but I promise it'll be very fast and you can ignore it if you like. But seriously though, so this talk is a little bit different from a lot of the stuff at LastCon. It's basically the antithesis of applications. Everything that's not an application of the network is probably what we're going to talk about today. And it's going to be a little bit encyclopedic in that we're kind of running through 1,000 different discovery techniques and different protocols and other kind of network weirdness, but it all kind of comes together with how do you discover things on modern networks today and how different is it from prior discovery techniques. So if you like getting deep into the weeds on weird SNMP fields and strange ways to reflect fields back from TCP send packets and all that fun stuff, this will be a fun talk. If you do not care about network stuff at all, this may be a little boring. Feel free to take a nap or go to the bar or anything else you like. So with that, I'll get started. So I work for Atreides. I work for critical research. On one hand, I do security testing, consulting, red team, all that fun stuff. Other hand, I've been building a network discovery product for the last year or so. We just went live about 25 days ago. So we have customers now. It's amazing. And it does basic asset inventory IT stuff. So that's kind of a lot of the work that you're seeing presented today has been driving the development of either security work or of the product that I work on as well. So why do we care about discovery in the first place? Well, if you're on a network and you're trying to figure out what the heck you have, that's step one of security in a lot of realms. If you look at a lot of the standards out there that require you to keep track of what you have, asset inventory is pretty much the very first thing you have to do to meet the security requirements of many standards. This is the kind of obvious thing is you can't secure what you don't know about, but also the fact that everything else builds on asset inventory. If you don't know what's on your network, you can't track patch levels, you can't track remediation, you don't know what stuff is pinging out to a third party, all kinds of fun stuff. So if you look at the way that older network discovery has been done, it's always been Active Directory-based, WMI, ping sweeping, running Nmap here and there. That doesn't really keep up anymore. So there's a couple of ways it doesn't keep up anymore. We'll go into that a little bit. But the key point here is there's definitely room for innovation in the network discovery space, and I'm hoping to contribute a little bit to that with what I'm talking about today and some of the open source tools we publish. If you look at external asset discovery, this is very much in the wheelhouse of LastCon, where if you're trying to figure out what a company has application-wise, and you want to break into it, because that's what we're doing, or at least defend it, you got to figure what's out there in the first place. And this used to be really difficult. It used to be you have to go trawl through all the old ARIN records and say, okay, find me every customer allocated ARIN block that happens to have this company name in it, but not that company name, but this one over here is spelled this way. It would take hours going through all the ARIN bulk data or going through who has records, trying to figure out exactly what a company has. These days, it's actually a lot easier. And the reason for that is it comes down to certificate transparency. Who's familiar with, show of hands for who's familiar with certificate transparency? Awesome. OK, CT is amazing. CT is amazing because every single certificate that you care about as a security tester or as a security person is going to be published on the internet almost in real time when it's registered. So every extended validation cert has to be registered with two different CT public logs as of last year to be part of Chrome. Now the great thing about that is every high-value website out there that has an EV cert is now immediately visible when that cert is published. So you don't have to go guess host names anymore. They're all published in the certificate transparency because that's where your subject alt names, your common name, all that stuff are posted. So CT is great. You can actually monitor CT in real time and find websites that are being registered as they're being registered. You can actually snipe these. You can find people setting up WordPress installations, and before the WordPress is even properly installed, they have to allocate an SL cert for it. Well, if you pull the CT registration, the SL cert out of the CT registration in real time, you can actually configure that WordPress site, backdoor it, install your own modules, then reset the configuration again afterwards before the user even sees it in the first place. And this happens automatically these days for things like GoDaddy and all these other third parties that set up WordPress sites on behalf of the users. The second that SL cert is published, it's now publicly visible on the internet, and you can snipe them to the first setup use case. So if you care about that stuff, there's a whole lot of talks on it, lots of cool research, speakerdeck.com, HDM. A lot of my old talks cover CT stuff and external discovery. This talk is not that. This talk is the inverse of that. We're going to talk about internal network discovery. So it used to be external was considered the hard part. External is all the stuff on the internet that might belong to your company. And we care about that stuff because that's how people generally break in. But what we're seeing is that visibility into internal environments has gotten much more difficult over the years. Especially if you're a company that has lots and lots of branch offices, lots of small sites, you've been involved in lots of M&A, you're a university where 90% of the equipment on your network is your student stuff, not yours. There's all these challenges with really complicated, really segmented, and really kind of distributed networks that were standard internal network discovery tools really stopped working years ago. If you look at how the network operations teams generally look at discovery, it's usually based on either SNMP or based on Telnet or SH CLI automation, using tools like NetBrains and Auvik and things like that, or all the SolarWinds stuff out there to do monitoring and detection. That sounds great, but what happens when you don't have SNMP credentials because it's part of an acquired company being attached to your environment and you just don't have credentials to it? Same thing goes for AD. Most of the IT inventory tools out there, whether it's another SolarWinds product or whether it's something else out there that does software inventory, those all require being able to log into those desktops, usually over port 445 through SMB, and authenticate it to using Active Directory credentials. If you don't have Active Directory credentials, well, you don't get that anymore. And even worse, what if you can't even connect to port 445 because your new security standard says all desktops must have the firewall enabled even internally? So as we move towards things like the kind of beyond corp security model, where we're hardening all of our desktops behind the firewall as well as outside of it, as more folks moving to the laptops, to BYOD, all of our typical discovery tools stop working entirely for internal. The fallback for all this, though, is a lot of companies are using things like Nmap and just straight ICMP pings to say, okay, here's the stuff that we don't know about. We can at least ping it with one of these tools. But they don't really go very far. Nmap is an amazing tool. I love Nmap. I've used it for, I think, almost 20 years now. What Nmap is great at is telling you exactly what services are running and exactly what kernel version is running on that system. It doesn't really tell you this thing's this particular access point, this is that switch, this is that printer. That's the level of coordination across all the fingerprints that Nmap doesn't do by itself. And there's lots of ways to wrap that. For example, the Metasploit software will wrap the Nmap XML and then use that to do additional identification on that, but it's not really the point of Nmap. Nmap doesn't do that type of identification. So the key point for all this is if most of the tools that do discovery today don't do it to give you discovery. They do it so they can sell you the thing they actually do. So that could be patch management, that could be monitoring, it could be inventory. But what they do is not discovery. What they do is something else, and discovery is how they get you there. So we talked about most of this. In addition to all the stuff we chatted about, there's also things like SDN, containers, clouds, virtualization. These are all throwing a monkey wrench into how folks do visibility and tracking internally today. As far as like how people are doing discovery, you'll see a lot of folks moving to passive discovery, things like NetFlow, which was a talk earlier about, talked a little bit about building your own NetFlow from traffic logs. You also see more folks using like centralized SDN type solutions where you're actually pulling SNMP from like Forescout solution where they actually do SNMP pulling of all their switches to find all the devices. So there's lots of new approaches that are being tried these days to help with internal discovery. But what nobody is doing, what there's very few innovation happening at all, is active scanning discovery. No one, it used to be back in the 90s, early 2000s, if you want to find stuff, you scan for it. You pinged it. You ran Nmap. You ran Nessus. You did something. These days, people are moving further and further away from active discovery because it's gotten much harder. The amount of information you can gather from a system on the network with a firewall turned on is very little compared to what it used to be. And a lot of folks have moved away from active discovery as a result. So the challenges with active discovery, of course, is if you have an authenticated discovery tool, it's spraying your password to everything on the network. Now, who here uses Responder as the first thing they do on a pen test? Okay, a couple folks. So Responder's great. It just passively listens to the network, waiting for someone to connect to it. So if you going into a new environment, you're about to do a pen test, you set up a laptop, you connect to the network, you run Responder, and you walk away. Sometime in the next 24 hours, there'll be a vuln scan, there'll be an IT asset inventory enumeration, there'll be a patch management tool, there'll be something out there that just connects to every computer in the network, gives you its password. And that's just how these tools work. They depend on something else logging into every single system on the internal network and giving it credentials it didn't have before, which is a huge security risk. Vuln scanners are notorious for this. Every time you run a Nessus scan with credentials, it's going to send you the stored credential to all those systems you try to connect to. And there's ways to limit your risk, ways to use reduced rights accounts and all that fun stuff. But most of the tools that do active scanning, especially credentialed ones, are security risks in that they expose your credentials to an untrusted third party on the same segment. You can man in the middle, lots of other fun stuff. Plus, they're not really as good anymore because of firewalling and so on. So if you look at the kind of new crop of security tools coming out for active discovery, they work a little bit differently. They're mostly focused on passive discovery techniques. They're not going to be looking at pinging your whole network and seeing how things respond. Instead, they're going to start off inside of your core network environment. They'll be pulling from your tap port. They'll be pulling NetFlow data. Companies like Senrio, Armis, Forescout, Clarity, et cetera. So it's a nice improvement for active discovery in that you see everything as long as it's talking, but there's some definite challenges to it. If you try to use passive discovery tools for an environment that you don't have access to, one that's multiple hops away, one that's on a remote site, it's really challenging just to get your net flow out of those devices in the first place. It's also really challenging to figure out, to coordinate with a remote IT team, things like that. They're also kind of expensive because unless you have remote access to that environment or you've got a device on the remote end or a virtual appliance on the remote end, it's hard to really capture the data you need for discovery. So these tools are great when you have the ability to do centralized deployments and when you can actually do remote site capture, but they start to fall down as soon as you get beyond that. So what we're really missing today is there's no great tools out there for like active discovery. And most of the research in active discovery really peaked in the late 90s, early 2000s. There used to be this huge zoo of network discovery tools out there. Everything from like Flash.c to Xprobe and POF, Queso, SynFP, all the AMAP. There's a bunch of THC tools, a bunch of ADM tools. Every hacker crew had their own little mini scanner they ran something for. There's old Legion tool from Rhino 9. There's all this stuff that used to exist. And now we've got Nmap. And Nmap's great because Nmap basically was an amoeba and gobbled up all those things. Just like Metasploit did with all the exploits of the world. It went through and implemented all of them. We've seen Nmap turn around and implement all the best techniques of all the old tools and bring them together. The challenge is there's not a lot of new stuff happening in active discovery space. A lot of the weird, obscure stuff, like, has anyone here run a Christmas scan in Nmap in the last 5 years? Besides Jagor? Okay. So, I mean, these are cool techniques, but they're not used very much anymore. But low-level fingerprinting stuff is actually more relevant than ever. All those like newfangled, Web 3.0, DevOps-y technologies out there, like your fancy SDN deployments, your containers, your containerized networking, all that stuff has like fingerprintable TCP stacks. It does stuff that's different. It does stuff that's weird compared to normal OS. Like all the fun, cool stuff we did back in the 90s to figure out whether something's Windows or Linux, it now applies to containers, now applies to virtualization, now applies to cloud environments. All the fingerprinting we did at the application layer also applies to things like load balancers and so on. So it's all coming back around again, but it's taking a while to get there. The one area where we are seeing decent success with passive fingerprinting is in the case of fingerprinting deployed directly to a router. So if you're using a fancy consumer router or a fancy business router with these features, it'll do things like DHCP fingerprinting directly on the router itself using a library like Fingerbank. And those are cool ways to say, okay, what kind of devices do I have in my environment? Is it this kind of phone or that kind of phone? The challenge with those solutions, though, is as soon as it can no longer see your DHCP client fingerprint, in other words, it's not on the same segment as your fingerprinting tool, it doesn't tell you much anymore. So sorry for the long rant, but the idea is like if we wanted to build an awesome thing that was active discovery based, it didn't require credentials, it didn't require having local tap port access, it didn't require layer 2 access to everything, and worked across everything, how would we go about doing it? And this is kind of what led me down the path of the research and the product dev stuff, but I'm here to talk about the research itself and some of the cool techniques you can do. So the challenge is it's very similar to running a vuln scanner. If you are going to rewrite Qualys or Nessus from scratch today, there's hundreds of thousands of vuln checks you'd have to implement just to get to the minimum bar. Discovery is not quite as bad, but there's definitely a lot of work that has to be done. You have to treat it the same way. You have to do a whole lot of research trying to figure out how can I send a really small probe to this device and have it respond back in a way that tells me that it's not this device, or it's this other device, or it's this version and not this other version. So it's very similar to pre-authenticated vulnerability scanning work. And that work is really expensive. The reason we've seen most vuln scan products switch to authenticated checks is because you can't keep up with unauthenticated scanning. Nessus does a pretty good job of that so far. They're one of the few vendors that actually tries to keep ahead of the pre-authenticated work, but they've got an entire dedicated team just doing that compared to the same size team doing all of the other 90% of their fingerprints. It's just a huge research effort. However, that's what I like doing, so I actually love this stuff. Let's actually treat this like a research project and look at this as doing applied research for the sake of device discovery at the same level that we've previously done for exploit development or vulnerability research. So starting off, this is one of my all-time favorite discovery technique I've been using since 1994, and I'll probably keep using until 2094 at this point, if I live that long. But so let's see. For folks who are familiar with NetBIOS 137 UDP probes, I think I've given the answer away here on the slide already, but so you can use them to, of course, find the host name of a system. You can use it to tell you the work group of a system. You can tell the MAC address of the system remotely if it's not Samba, not faking out the MAC address. But there's the second query you can do. When you scan a system on the network for NetBIOS UDP over 137, you say, hey, what's your name? The device will come back saying, my name is Bob. OK, great, Bob. If you go back and then query that system again saying, hey, Bob, what are your IP addresses? It'll actually come back with a list of all its IPv4 interfaces. Now, the really cool thing about that, those are the current active interfaces, including VPN adapters, cloud adapters, virtualization adapters, all that fun stuff. So you can find all your systems running a VMware virtualization stack on the local network using a single unauthenticated UDP probe to broadcast. It works great. You also get the MAC address back, which tells you more things about the environment. You can tell if the device is on a VPN. You can tell what the VPN IP address is. So if you're trying to figure out, is this device currently connected to a VPC using Amazon's VPN client, as long as you don't have the firewall enabled on Windows, it'll actually tell you through a single unauthenticated UDP packet. So I love this stuff. So I've been using this for years to figure out how to do multi-home host discovery. So you're trying to figure out how to break into the PCI, CDE, or some other sensitive environment from the network that you're currently on. You can scan the subnet via NetBIOS, find any device comes back saying it has an IP in that other subnet as well, and then break into that box, because that box will get you where you want to go. So there's an open source tool for this. If you want to play for it, it's github.com, HDN nextnet. And this does NetBIOS queries really quickly and sprays packets out and gets you MAC addresses and all the IPs coming back in, and a great way to find all your multi-home boxes when things are in kind of their default configuration. So skipping ahead a bit, if you're trying to figure out how to find more information, then opportunistic SNP. We've all used SNP for discovery at some point. SNP is like the stupid brother printer that I just bought has a driver that installs that SNP gets and sets by default on every network you join. So I was looking at the Wireshark traffic, this laptop I plugged into the last client network, and I'm seeing it do SNP set requests to random devices in the local subnet. I'm like, what the heck, man? Like, this is just the printer driver doing it all by itself. So the cool thing about that, though, is they assume that SNP is going to be enabled on every printer, and they're going to assume that version 2 is enabled with the community string of public. So great, let's abuse that. How do we figure out how to get the most information from SNP as possible? Not in a, like, oh, I'm going to steal your password or steal your LDAP credentials, which are all great things you can do with it, but how do I just get, like, basic discovery information out of these devices that are SNP enabled? So you can pull things out like the ARP cache. You can find the neighbors of the device by pulling its ARP cache. You can dump the MAC and VLAN tables in with switches really quickly, which gives you the full port topology, gives you a list of every other client connected to the same environment. You can find devices that are completely firewalled off because you can then find their MAC address in the port table and say, okay, but I got the MAC, but where's the IP, and keep looking for it. So it's a little bit limited, but there's a lot of really cool benefits when you do happen to find a SNP-enabled device somewhere in your attack environment, your target environment, because it'll tell you about all of its neighbors. SNP really is the narc of the IT world. So here's an example here. If you want to dump the IT cache, this is telling us the MAC addresses of all the workstations in the same local network just by pulling the ARP cache of the printer. So as long as you get a printer somewhere, it's going to dump you all the information. So we're going to build on this example. We're going to make this like the base of our fort that we're going to build on top of this little kernel of information because it's so much fun to mess with. So you can take that base example a second ago, where you do SNP polling of this particular MIB, and say, great, this will tell me anything that's currently in the ARP cache of the printer. Well, what's in the ARP cache of the printer? Obviously, anything that talks to the printer is going to be in the ARP cache. As long as it's polled in the last 5 minutes or so, it'll be in the ARP cache of it. So all your workstations that have an active connection to that printer, their MAC addresses will show up in that printer. So if you dump the ARP cache of the printer, it's not just telling you, here's the IP and here's the MAC of things that are nearby. It's saying, here's the IP and here's the MAC of devices that are talking to this specific printer right now. So you know which systems are probably workstations that have a printer installed. And you know which ones are tied to what printers. So you're getting connection information out of it as well. You're not just getting the ARP cache. So let's build on a bit. Let's say we wanted to enumerate the remote subnet, the MAC addresses of a remote subnet. We can't do an ARP scan because it's across a firewall. We can get the ARP cache normally, but the ARP cache will only tell us things that are currently in the ARP cache. That's not really enough to tell us. We want to find everything, not just what's currently talking to the printer today. So how do we force things to talk to the printer remotely? Well, the really easy mode is you spoof IPs. You say, okay, I'm in 192.168.0.whatever. My printer's in 192.168.1.whatever. Let me spoof traffic from 1 to the printer from every source IP of the destination subnet, and you'll cause all the reflected replies that end up in the ARP cache. So using let's see if I got an example here. Yeah, so using Nmap, for example, with the send IP option, spoofing your SNP host, scanning your target network like that, you'll actually force populate the ARP cache of the printer with all the devices in the remote subnet, and then you can dump the ARP cache, then you get them all. So now we've got a remote ARP scan built on the fact that we've got a printer sitting in this environment. The challenge with this, though, is it doesn't work if you've got RP filter 1 or RP 4 equals 0 on Linux routers. So if you've got a Linux-based router between you and that subnet, a lot of those get dropped on the floor. However, if you've got a standard like Netgear or some switch or a layer 3 switch involved, they generally pass the traffic right through unless you've got egress filters on both sides. So another way you can do it, let's say you can't spoof traffic, because spoofing traffic is an easy way to do this stuff. We have to go a little harder. So two guys on the Talos team, Martin and Alexander, had a really cool technique of using UPnP notify requests to leak IPv6 addresses of IPv4 subnets. So what they would do is they'd send a UPnP request to every system on the network, and they'd say, hey, UPnP thingy, I want you to notify my UPnP endpoint, but I want you to notify this host name that resolves to a v6 address instead. And so they cause all the v4 devices on the whole internet to then connect to a v6 address of their choice, and then they can figure out which IPv6 addresses went to which IPv4 devices. So it's really cool research. However, we can abuse that for remote ARP spoofing. We can say, let's do a UPnP notify to every device inside the system, inside the local network, telling it to talk to my printer, and then vice versa. And we can use that to slowly build up the ARP cache of the printer, then dump the ARP cache again, and then we have all the Macs. So it's another way to basically force populate the ARP cache using UPnP notify request. Another way you can do it, this works better for most corporate environments where you've got SIP phones, like IP phones in the environment. You can do SIP notifies and SIP invites to force calls between devices that then reflect back to the printer because the destination endpoint of the call is specified in the UDP payload, not in the transport layer. So you can send a UDP payload to a phone saying, I'm making a phone call to your phone, and I want you to call me back at this other IP, and that other IP is the printer. Now you're populating the ARP cache of all your phones. You can also use it to find some of the desktops as well. So this is a cool technique. This is notified by Rick Lachey of Trend Micro. I'm not sure he's here today, but local guy here did some awesome work on it. So moving on to SNP. I know I'm going to hopefully beat this dead horse all the way into the ground here, but SNP v1 is really neat. The challenge with v1, which is the really, really, really old version of SNP, is that it has very few features. You can only request one OID at a time, or generally you can't do a get bulk request, which is the fast way to query stuff. You can only single OIDs. What you can do, though, is you can stack multiple OIDs into the same GET request at the same time, and almost every implementation out there will support this. So if the device only supports version 1 and it's really slow, you can still stack multiple OID requests into the same packet. The problem is there's no user-land tools that do this. You have to actually get into the wire level and actually stack all things together and do all the bear encoding, all kind of junk in SNP. So here's an example of what a packet looks like when you request 15 items in the same SNP v1 size. The only real limit on this is the response packet has to be smaller than the maximum set on the SNP server side, which is anywhere between 500 to 1400 bytes, depending on the implementation. So you get a lot of data. The neat thing about this, though, is let's say you wanted to enumerate every IP address of an SNP device, but with just one packet. Or let's say there's a whole bunch of really sensitive OID MIBs that you want to query, things like the stored LDAT password, the stored telnet password. You want to pull the ARP cache entries. You want to pull anything you want to pull out of SNP. You can now query about 15 of these at the exact same time with a single packet and spray that packet across the entire environment. So instead of having to first scan for SNP and then go back and query all these through a really slow SNP walk that is one query at a time, you get it all in exactly one packet really quickly. It's also good for DDoS. Same thing for get walk. So get bulk actually has the same attribute. Get bulk, get bulk is the way that you query multiple OIDs at once in SNP version 2. So it's only supported in version 2 and version 3. It queries an entire range of OIDs starting at a particular entry and then moving to the maximum value you set. But the cool thing about this, you can also stack those. You can put multiple get bulk queries into the same packet, and most devices, except for the IBM i-series mainframes, will respond to this just fine. And again, it's great for DDoS because you can get like a 1500 byte or even in some cases 6500 byte fragmented UDP packet as a response to one of these things by pulling a whole bunch of tables at the same time. So it's really neat. You can actually do, you can basically enumerate, you can dump every IP address, every MAC address, every ARP cache entry at the same time in the same packet across most environments with one packet. And the speed is ridiculous. So if you're going from let's do a quick scan and followed by a walk to doing a single packet, this is saving you about 50 packets in about 20, 30 seconds per host. Let's see, here's an example of that. So grabbing all the MACs, all IPs, you've got 3 OIDs stacked here. These are 3 get bulks in a row, and each one of these is pulling an entire table from the remote device. So here's the first chance to win a Tradus t-shirt that is only slightly wrinkled looking. So I got squished in my bag over here. But basically, I only have size large. I apologize. But if you would like a size large shirt and you can answer this question, for SNP version 3, what does it tell you if you can't authenticate to it? You don't have a valid password. So SNP 3 requires authentication, requires an 8-byte or more password for either auth-priv or for the privacy password. So what do you get from SNP version 3 if you can't authenticate, besides the fact that it's SNP version 3? Oh yeah, bad error message, bad passwords. Close. Any other guesses? Okay, well, that was actually a close enough answer. You get a shirt. Sure. Where'd you go? Oh, thanks, sir. So SNP version 3 has what's called an engine ID. An engine ID is this kind of opaque identifier, a bunch of big bag of bytes, basically, that says, if you want to talk to me, you have to authenticate to me, and you have to use this engine ID as part of the challenge and authentication process. So what very few people seem to know on the pentest side is you can do user enumeration through SNP version 3. There's a tool called the SNP Pwn, or SNPwn, if you want to call it that, which will go through and brute list the list of usernames to tell you which usernames are valid, even without knowing the password. So that's a great thing you do. So you can get the username out. Now, why do you care about a username? Well, maybe the username will tell you that the same username is valid on these 5 routers, but that username is not valid on these other 5 routers. Well, which ones are ISP managed? Now we know. So it gives you a great way to say who operates, who manages these routers versus these other routers or switches. But that's not what we're going to talk about. The engine ID actually has some other useful fields in it. So as gentleman mentioned before, there's some error fields that come back out. They're actually really interesting. So you get invalid engine ID count is the number of times something's tried to authenticate to it and failed. So you can get the bad authentication counter out of it unauthenticated. You get the engine time, you get the boot size, you get the max size. But the really interesting thing here is the engine ID itself, which is this giant blob up there. You can see, I don't know how visible it is, but essentially it's this giant blob of bytes which has a type field. The type could be something like MAC address or text field or octets. But what we really care about is what's in that blob itself, because that blob will give us the enterprise ID, which tells you the manufacturer of the device for sure. So even with nothing else, we're getting back the manufacturer. We can tell whether it's a Cisco device, and it was Cisco because they bought some other device. Their wireless LAN controllers come back with a different engine ID than the rest of them. Sometimes the MAC address doesn't actually match the engine ID because of acquisitions. But the thing that really, really matters here, and the thing that we're going to abuse the crap out of, is that MAC address. So essentially, even if you can't authenticate to a device through SMP version 3, you can get its MAC address remotely without authentication. However, getting the MAC address out is really tricky. It depends on the type of equipment. Some of them return the MAC address as the last 6 bytes of the engine ID field. Some of them do almost like EUI64 encoding, where they put an FFFE in the middle of it between bytes 4 and 2. Some of them are everything but the last 1 byte. Some are everything but the last 2 bytes. So you have to actually figure it out. You have to go through the millions and millions of replies. So we did polled the entire internet, got about 22 million of these things, dug through them all, and figured out how they're all formatted, and then built rules to map them all. So that's kind of where we ended up. Not only do you get the MAC address to these systems, but in cases where it's based on the net SNP open source software, you get a very different response, which is called a random ID. And the random IDs are pretty cool because it'll actually tell you, is this device uniquely this host or is it a different host? So if you're trying to find a multi-home device and you do an SMV3 scan, you'll get back all these random IDs from net SNP hosts. Anytime those random IDs are the same between multiple hosts, you know it's probably the same device. So now you've identified multi-home devices based on a wide scan by correlating unique values. So switching gears again real quick, way back in like 2004 or so, I got pulled into a project where we're trying to identify, it was a large radio station network, and the DJs were selling rogue ads in return for unmonitored internet links from each radio station, because they wanted to like look at porn and do things like that. So they were getting in trouble with corporate because they're supposed to go through corporate for their corporate proxy. So I got pulled into this job where we had to go find all of the egress points of this network from internally, but we couldn't physically go to the sites. We didn't have any privileged access to anything. We had no credentials to anything because these are just like random DJs, Windows 98, or I guess at this point, Windows Vista boxes maybe a little too early for that. But essentially, we had to find out all the different egress points of the network, and we had to do it without credentials and from a central scanning location, and turn into a whole fun project. Where we ended up with this, the very first thing we did is we ran basically a spoofed SYN scan. So if you're going to send a SYN packet to every system in the internal network, and you're going to send it from an internet host, even though you're sending it on the internal network, the internal host will reply to that external host as if it's local and route it out its default route. So if that default route happens to go out a different interface than the one you're monitoring, and it comes back into your internet-facing host, you now know all the points of your network where traffic is leaving your network through other internet connections besides the one that you know about. So you can find VPN adapters that are default gateways. Back then, it was things like AOL dial-up would change your default route. So if you find a machine on the local network that had an AOL adapter and you scanned it, you'd actually see the packet coming back out of AOL instead. And the trick for this was we encoded the sequence number of the TCP packet itself, had the internal IP encoded as the same 32-bit value. So when we got the SYN ACK back, we just decremented one from that gave us the internal IP. We busted that DJ for having AOL installed. The challenge, though, was with spoofing this traffic, it doesn't like to cross firewalls very well, because anytime you hit egress filters on one side of another firewall, it'll drop your packets. So we played around with a couple of ways to do it. You can do ICMP as well. You can spoof ICMP where you encode like an encoded version of the initial destination into the ICMP data packet, spray that across the entire environment from an external host, look for the ICMP echoes coming back out, and then basically fingerprint them and then bust them. So it worked okay. The problem was as soon as the firewalls, stateful firewalls that either managed ICMP state or TCP sequence states or did egress detection would break that. So we're looking at what are some other ways we can go and improve that technique from 13 years ago and make it better today, or however long it's been. It's been a long time. So NAT filters could drop this stuff, but UDP payloads actually work a lot better. We can use things like UPnP notify. You can use like all the other UDP stuff we talked about, like NetBIOS, and we can basically spoof those packets internally, just like we did before, or spoof the UPnP notify destination to be the internet-facing IP, listen on the internet side, and get it back. So here's an example of using ZMAP, kind of a modern take on that. So we're going to use ZMAP internally to scan for the NetBIOS port. We're going to use that NetBIOS ping packet that it ships with. That's one of the ones we contributed to it back in the day. And then on the internet side, we're going to listen for anything on port 137. And we can actually see internal hosts are responding back to us. Now, the cool thing about this is the source port's 137, but the destination port's not. So your firewall is dropping outbound 137. That's fine, because it's coming back out somewhere else. It's a reply to it. It's not the inbound. So most firewalls actually allow this traffic out, but to them it just looks like a weird source port going out to a high UDP port, but in reality it's a full UDP reply leaking back to the MAC address, IPS, hostname, workgroup, et cetera. So that's a cool technique for UDP that I still use today. Let's see how we have time. Oh, I need to start flying through this. 30 slides, we've got about 90 more to go. We can do this. I'm kidding, we'll go a little faster though. So DNS is cool, all right. Before I switch to DNS, I need to figure out how to get rid of this t-shirt. Does anyone here know what eDNS0 is? eDNS0, it's an extension to the DNS protocol called eDNS0. Sorry, I don't see any hands up. Did I miss anybody? All right. Easier one. If you use one of those big DNS gateways out there, like 1111 or 88888, how does the final upstream DNS server or the website you're actually trying to go to know which region to serve you from? How does it do anycast routing? How does it find you the most geographically close system for you? Because keep in mind, the DNS servers you're talking to the DNS server. The DNS server, the caching DNS server is going to make a request on your behalf, but it's not doing it from your IP. It's doing it using its IPs. It's going upstream someplace else, querying your authoritative server. That's coming back and telling you where to go to. How does that authoritative server know where you are to give you the closest server to talk to? Yes, similar. Close enough, you get a t-shirt. So eDNS0 is an extension for DNS that increases the maximum size of the packet, but also supports something called client subnet discovery. So what happens is if you use the 8.8.8 DNS server, Google's a narc. Google will actually take your internal IP address, staple it onto the DNS packet, and forward it upstream to authoritative DNS server, who can then see, oh, this is where the user's really coming from, and then route you to the right response based on that. So they're actually taking your internal IP and sending it off to the real upstream DNS provider. However, they don't just send it directly. What they do instead is they encode just the /24. So it's okay, Google's not telling you your exact IP, just what /24 you're coming from, which is the same thing. So the cool thing about this, if you're doing a pen test or a security audit and you run your own custom subdomain, like a lot of folks do for Burp Collaborator or things like that, it tells you a lot of information about the environment. If you can query any DNS server or you can force an internal client to make a DNS request on your behalf, you can learn a ton of information about the environment without doing really any work besides listening for an inbound DNS request. So the way this works is you'd set up a new fake subdomain like blah, blah, blah.mydomain.com and set the NS record for that domain to point to an IP address you can monitor, something like a DigitalOcean, VPS node, something like that. And all you do is sniff for traffic coming in and see what happens. So you do something like this. You do a dig request of your encoded string at your helper domain at the target. The target then queries its upstream resolvers that then eventually query your server and then times out and gets fussy about it. But in doing so, it actually does all this fun stuff. So you can actually put timestamps in these packets and have your final server echo back the timestamp it received and do a full round trip time. So you can actually build cool trace routes into DNS doing this. Let's see. We can also figure out which resolvers a given internal machine is using. So if we query an internal box saying, look up my custom domain, it's going to query its resolver. The resolver is going to query us. We can then see that query and respond back saying, we were queried by this resolver in the DNS packet itself. So we can actually tell you where the DNS request came from. And in other words, we can determine whether that particular internal DNS implementation or that client internally is using the proper DNS server or a rogue DNS server or something else. So this tells us a lot of cases like where this stuff comes from. So where this was used heavily was the Nebraska child pornography case where they busted a bunch of people. They used this thing called decloak.net. They used the same backend code as decloak, which is something I wrote a long, long time ago, mostly to bust Tor users. And it did things like this. It would use upstream DNS to correlate your ISP back to your IP. So even if all your proxies are set up properly, if you could force your client to make a DNS request, it could then leak out your real ISP as a result. This is one of the techniques that's used by that toolkit for busting this child porn ring. So I think we talked about most of this. You can do things like you can identify weak transaction IDs, static source ports, other things like that. There's code base. The code for this is at github.com, HTML rumble-tools, but I'll point to it later. So you can, if you query, let's see, if you query 8.8.8, upstream resolvers that come back are not 8.8.8. They're actually coming out of another anycasted IP. So you won't see a source query coming back out of 8.8.8. You will see a query coming out of one of these source IPs. So the difference between Cloudflare and Google in this case, kind of an aside, is that Cloudflare does not use the client subnet DNS, the client subnet extension to leak your IP. What they do instead is they say, based on the IP address that you see coming back out the other end of it, that correlates to the regional provider that you should serve your request to. So they can still tell you the general region of it based on which Cloudflare POP is the one querying you, but they don't actually leak your actual /24 in the process. So I'm going to skip ahead, but basically if you want to filter, make your DNS requests work, you have to constantly encode them with random IDs, otherwise they get filtered and caches break all of our testing. So if you want to dig in, let's see, same thing. So there's one I'm trying to cover today, but there's a blog post on it, the rumble.run website. But essentially, you can use DNS as a remote blind port scanner or a ping scanner. You can force a DNS resolver that has access to a network that you don't have access to make queries that bounce against your NS server that then tell it to resolve to another name server inside the internal network. And just about every DNS server will make these requests before you. So if you scan like the 9.9.9.9 public DNS server, you can actually use that server to scan its internal Amazon VPCs and figure out which devices on their internal private subnets exist, which ones don't, based on timing responses. So that's all inside of a blog post at the rumble.run blog at this point. But let's see, skipping ahead, client subnet stuff. All right, so moving on to MAC addresses. We talked about lots of ways to get MAC addresses before via SNMP, via NetBIOS, but there's lots of other ways to do it. What there hasn't really been, though, is a lot of talk about how to fingerprint a MAC address. Obviously, the first 3 bytes means the vendor, and therefore you can look at the vendor, you get the rest. But that's actually no longer true. Used to be the first 3 bytes indicated the vendor. Now it's up to the first 44 bits can be used to determine the vendor. And there's a lot of netmask now. There are /36s, as well as /28s and /24s. 24 netmask is your standard 3 bytes. Then 28, 36 are extensions on top of that. So they're chopping up the MAC address space just like we've chopped up the IPv4 space as they start to run out. So you can buy much smaller MAC address ranges now. So the cool thing about this is because these MAC address ranges are much smaller, more of them are being issued. Every time Google wants to make a new device, whether it's a Chromecast or a Pixelbook or a Pixel 4 or something like that, all the vendors that have any kind of networking equipment inside their chipsets, whether it's Bluetooth, wireless, Ethernet, they all have to go get another range of MAC addresses on the fly. And when they go get that range of MAC addresses, what they're doing is actually telling you something. They're telling you any device with a MAC address in this range, it was manufactured at least from this date or later. So you can use, let's see, we'll cover it, well, probably won't have time, but we can dig into it later. But essentially, given the MAC address and given a database of all the historical OUI registrations for a given MAC prefix, you can tell exactly how old the device is. And that's really useful in some cases for finding older stuff in your network or newer phones. Or actually doing very specific fingerprinting. So that work's going to be happening with the DMAC project along with the stuff I've been working on. Hopefully we'll have a whole lot of much better fingerprints for MAC addresses soon. So moving on a little bit, MDNS is one of my favorite protocols because it tells you so much information. MDNS is one of the very few network services you'll find running by default on an Android phone on the local Wi-Fi. So if you scan the network right now with all of our phones connected to the Wi-Fi, every one of us running Android, or majority of them will, actually respond to MDNS, and they'll respond to a pointer lookup packet for its own IP address. And in doing so, they'll tell us the host name of our own device, which often is just the word Android. So now we've got a great, almost pretty much surefire way to determine if it's an Android device or not over the network by default with mobile devices on a standard network, even with all the security settings in place. Mac OS actually returns all kinds of cool stuff. Actually, almost all Apple devices do. Everything but the most recent iPhones and iPads will return the exact device model, the screen size, all kinds of fun stuff, along with the OS version, just from MDNS queries. Printers are the worst. Printers will give everything from like a picture of the printer itself all the way to the type of ink it's using. Everything comes up MDNS. MDNS is great for those. So here's an example of doing a local discovery of MDNS where there's a local Mac Mini. This is all the information coming back from a Mac Mini on a local subnet. You get the name of the computer, you get what services is running, RFB for VNC, SFTP, SMB, et cetera, the pointer lookup. You actually get the, well, this one doesn't have it, but you get the IPv4 address in this case. But what you also get out of this oftentimes is the actual full MAC address. And if it doesn't have the explicit MAC address in it, it'll give you an IPv6 address that's encoded to the EOI64 address, EOI64 format, which has the MAC address embedded in the v6 address. So there's lots of different ways to pull the MAC address out of these things. Here's some examples of just common devices. Your Android phones will tell you it's Android. IP cameras give you very specific service names that tell you what vendor they are. Printers tell you the MAC directly. Sonos devices are great at giving you the MAC addresses directly as well. All right, so moving on to more techniques before we run out of time. TLS certificates, default SSL certificates, not necessarily the ones at port 443 where you normally go to, but the ones in all the other ports that some of these devices have running on them tell you a ton of information about the device. They'll tell you everything from the MAC address to manufacturing date, serial number to the Dell service tag. If you want to go get support for somebody else's Fortinet device, you can just scan it, get the MAC address, get the certificate from one of the higher ports like 8900, use that to get the serial number, talk to them, and you can get support and firmware and updates and all that stuff. You can also do things like get the service tag for Dell products, and once you have a service tag for a Dell product, you can then look up the full specs of that hardware, how many processors it has, how much RAM it has, when it was manufactured, the hard drive size, all that fun stuff. Even sometimes the software stack and what software was installed as part of it. So lots of really cool fingerprinting stuff comes out of TLS fingerprints. We recently added about, I want to say 100 fingerprints to the open source Recog project. I think it's listed. Yeah, that project in that URL there, that's the backend database for Nexpose, Metasploit, Metasploit Pro, Rumble. We contribute a ton to it just because it's what we use as a primary data source. It's open source, it's BSD licensed, it's free. Feel free to use it for your own stuff. But we added a ton of TLS fingerprints recently. Here's some examples of what cool things you can do with TLS fingerprints. So obviously for Ubiquiti equipment, you can see the full MAC address right there in the CN field. That's easy. Synology, you can fingerprint, okay, it's a NAS device, that's great. The Google Cast one's really fun here. So that's a Google Chromecast. The first part's a serial number, the 4Y3ZXB bit. The next one's funny though, because that's FA8FCA. That looks like a MAC address, but if you put that directly into a MAC address to look up, it says no valid MAC address. If you want a lovely Atreides hoodie, tell me why that's not a MAC address and how to make it a valid MAC address. It doesn't mean adding colons. Like there's one tiny thing you have to do and this becomes a valid MAC address. What's that? Colons? No colons, not reversing, not colons. Almost, okay, so.
Is it the Indianness?
Almost. There's so a normal MAC address is called a global MAC address, or basically just like IPs, you've got a multicast and a non-multicast field. If you have a local only MAC address, you flip one bit. So that F8 becomes an FA. So if you drop that that FA becomes an F8, and then if you look at that F8 address, it's actually the valid Bluetooth MAC address of the Google Chromecast. So we're getting the Bluetooth MAC address of the Chromecast over the network from a TLS certificate, but only if you know how to flip that second local bit. So it's kind of an obscure one, but an odd one there. Also fingerprint your Palo Altos, your network firewalls, things like that. So moving on a little bit to network manufacturer discovery protocols. There's lots of really cool ones out there. Brother Printers, like I mentioned before, has a ton of them. Ubiquiti has one that's on all of Shodan. Some are broadcast only, some actually go across the whole internet. The Ubiquiti one's really fun because it tells you the full MAC address, tells you the firmware versions, it tells you lots of great information about the device. The actual name of it, like direct-Carl. You know it's Carl's box. So things like that. You get tons of information out of these manufacturer-specific discovery protocols, and people very rarely scan for them because they're a pain in the ass to scan for. Like Nmap doesn't do any UDP discovery by default. Even if you specify UDP ports on it, it's generally doing very directed probes. It's not doing UDP-based manufacturer-specific discovery probes. This is a great way to get lots of information. So Shodan's been getting better at scanning these lately, but very few other tools out there do this today. Let's see. So just doing a quick rundown of other things you can pull MAC addresses from. With a product I've been playing with a little bit, we get MAC addresses from about 10% of the whole internet. We can pull the MAC address out remotely with no authentication. And we get these things out of things like SNMP with no authentication out of the engine ID field, version 2 of SNMP when the community string is available, MTNS, EY64 IPs, device-specific protocols, SSDP, DHCP hostname pointers, HTML pages, NetBIOS replies, TLS certs. There's like 1,000 ways you can pull something's MAC address. And once you have its MAC address, then you know how old it is, and you know what vendor it belongs to. You know almost what batch of devices it was in. You probably know what firmware it's running. So MAC addresses are great, but you have to really go beyond layer 2 to really work with them. So we talked about most of the stuff. Some projects here, I keep track of how old every MAC address prefix on the internet is. There's a GitHub repo, you can pull it down as a CSV file and tie that into your own stuff. So the Mac Ages project. Also work on the full OUI registry, the IEEE registry of all the OUI prefixes. You want to play with the raw data historically. This includes the DeepMap project, the Wireshark archives. It merges it all together in one big ass JSON database. You can grab the full daily updated JSON from that as well if you really care about this stuff. And keep in mind, this stuff is shared between Bluetooth, Wi-Fi, Ethernet, as well as things like fiber channel adapters. All use the same namespace. So just because you have a Mac doesn't mean it's Ethernet. It could be anything. I talked a little bit about multi-home device discovery earlier, and there's lots of other ways to do it besides just NetBIOS. This stuff is pretty important because you're trying to figure out how do I get from a high security or low security environment to a high security environment. How do I get past segmentation? How do I find people with particular nodes in place? So just like with MAC addresses, you can pull extra IP addresses out of lots of different protocols. You can see HTTP redirects to an IP address that's in a different subnet. You can find TLS certificates that have the IP address embedded in them. You can find MDNS replies that have other IPs other than the one you're scanning listed in the response. V6 subnets you know are probably enabled. SNMP, of course, will give you all the adapters on the device, including ones remote subnets. Once you identify devices that have these multi-homed interfaces online, you can then use them to basically pivot through the device and then bypass network segmentation. So here's an example of a Fortune, we'll call them Fortune 50 company's internal environment, just a small subset of it. Every red dot on this screen is an IPv4 external subnet. So these are all internet-facing IP addresses you can reach from the internet today. Every one of those little black dots there, that's a device bridging at least one of these external subnets to one of those green dots, and all those green dots are internal subnets. So pretty much from anywhere on the internet, you can get to anyone to their internal environment and vice versa 1,000 different ways. This is how much of a pincushion most corporate environments are. And this entire graph was pulled from an unauthenticated internal scan of only part of their environment. Just to give you an idea of like how much bridging happens in the real world. Now, these devices may all be fine. Every one of these little black dots may be a device with good hardening and no routing enabled and lots of forwarding turned off and all that stuff. My guess is at least one of them isn't. And all it takes is one of those suckers to get from one network to the next network to the next network. And you can see how interconnected they all are right there. These are all those little black dots and everything on the screen here. These are only devices that we could determine were multi-homed by pulling information out of them unauthenticated using a standard protocol that we just talked about. So moving on a little bit more, and then finally the last thing here before we break. One thing that's really important to do on network analysis is trying to identify, is this device the same as some other device? Is this unique? Is this a multi-home device? Is it part of multiple things? Like, let's say you can't get a particular interface to tell you more than one IP, but you can say, what is this device, and is it similar to this other device over here, and use that to build up a multi-home list. So if you can positively correlate this device to that device being the same physical system, then you know it's multi-home because it has to be. So there's lots of unique things out there you can use for it. You can use MAC addresses are a pretty good starting point when you got those. Sometimes they're not unique though. TLS certificates are sometimes unique. DNS host names are unique. But it gets hard. So given a wide enough view, how unique are these things in the real world? Well, MAC addresses tend to overlap a little bit. There's lots of bogus ones out there. You tend to have network storage devices use shared private IP addresses for their cluster backends, and those tend to overlap as well. But there are some pretty cool things out there. So the ones that we're using today that work really well are non-blacklisted MAC addresses, the NTLM SSP DNS computer name that comes out of the NetBIOS replies, with the one that's the full corporate .LAN domain. That's a pretty good unique identifier. This stuff is also really valuable if you're doing DHCP tracking. If you're trying to figure out whether the host over here is the same host you saw last week, these fields are pretty much a guarantee that the device is actually the same thing. The one I like the best lately, because if you follow all the guidelines and turn off SMB, how do you still find out if the device is the same one? Well, ends up the remote desktop protocol has a TLS certificate, and that certificate is valid for about 8 months or so by default. But as long as you're scanning within that 8-month window, you can follow that unique signature of that fingerprint of that certificate, and it'll tell you whether it's the same device or not, even as it moves between your wireless LAN and your corporate networks. And of course, for net SNMP-based SNMP implementations, that random ID, which is available pre-authentication through version 3's Engine ID, you can use that as well to confirm that a device is unique or not. So some examples here. If you scan all of Iceland, as one does, we have about 4.3 million IPs. We scanned them all in a few hours, and then we said, okay, which ones of these actually overlap? Which of these are multi-homed? We found a couple of routers on the Icelandic IP space that bridge multiple /8s, and we knew they're the exact same device because we found at least one unique field that tied them all together again. So you can see a device here. This one crosses 178 and 213. One down here crosses 157, 194, 213. We know it's all the same device because they're all part of the same scope. And on the right side there, this is one that had like 200 and something IP interfaces on it. And we actually verified this is actually the same router. If you cause an authentication error on one of those interfaces, you'll see the counter get updated in the other interface someplace else. So you can actually verify that these are actually the same device. So let's say I wanted to like turn off parts of Iceland. That router would be a really good candidate. You knock that sucker offline, and a large portion of their environment goes offline. So even without doing a full trace route or having like routing topology, we know that device is important. We know it's bridging multiple segments, and we know here's all the different ways that you can get this device from the internet. So that's pretty much it. Discovery's not dead. If you care about this stuff, like reach out, talk to me. I love to collaborate and stuff. I like working fingerprints, protocols, open source tools. I worked on Metasploit forever. I'm going to work on this forever too. The Recog repo is the best open source fingerprint database for any kind of application layer fingerprinting that I know of. DeepMac is where we're going to be doing all the MAC address specific fingerprinting, and all the Rumble specific stuff is going to be that Rumble tools repository. That includes like our DNS, remote ping scan tools, and things like that. I still have a hoodie to give away. Who showed up today and did not have a jacket? Did anyone not have a jacket? There we go, first one I saw. All right, sir. We try to keep people warm here in Texas. Here we go. You're welcome. Awesome, no questions. Thank you very much. Have a good day.